Today's topic is moving coil galvanometer. Now this moving coil galvanometer is based on the principle as a torque acting on the current flow. So in the previous lecture we have seen torque acting on the current flow. Tau dash is equal to number of turns, current I, area of the coil, magnetic induction into sin theta. And this torque acting on current flow, this principle is used in the device which is called as a moving coil galvanometer. Now where this moving coil galvanometer, these moving coil galvanometers are used in the analog ammeter and voltmeter. Now already all of you are knowing ammeter and voltmeter. So ammeter is a current measuring device, voltmeter is the voltage measuring device, but analog. But nowadays digital voltmeter and ammeters are used. So these moving coil galvanometer are not used in the digital ammeter and voltmeter, but it is used in the analog ammeter and voltmeter. Means the ammeter and voltmeter which you are using in the lab to measure your current as well as voltage. Now what that moving coil galvanometer, what is the construction of that moving coil galvanometer? This moving coil galvanometer consists of concave pole pieces of the magnet as a north pole and south pole. Now why this concave pole pieces of the magnet? This concave pole pieces of the magnet provides a radial magnetic field of induction B. In this radial magnetic field there is a core, and over this core a coil is wounded having certain number of turns. So this central part is to be called as a core. Over the core this rectangular coil is wounded having number of turns, and one side of the wire of that coil is attached to a mirror, suspension mirror, and other side of the rectangular wire is to be connected to the spring, which will called as a suspension spring. Now what happens here, the current will get entered in the rectangular coil through this fiber. This fiber is made up of phosphorus bronze. As the current gets entered inside this rectangular coil, current starts flowing through this rectangular coil. Rectangular coil is placed in the radial magnetic field. This radial magnetic field will be useful for, due to this radial magnetic field, the plane of the coil is everywhere at any position of the rotation. Plane of the coil will be always remain parallel to the magnetic field, and therefore the torque acting on the coil will become maximum. Now torque become maximum means what? Your tau dash, which is equal to number of turns, area I into B sin theta. Now torque acting will be become as a maximum due to radial magnetic field, means your sin theta term reduces to 1, and your torque will become as a NAIB. This torque forces that the coil start performing a deflection inside this radial magnetic field. Due to that deflection, there will be a restoring torque which will get developed due to the spring, and that spring gives us a restoring torque, and that restoring torque I can say as a tau 2 double dash, which is directly proportional to the deflection of the coil, that is phi. So that restoring torque can be written as a K into phi. At equilibrium position of this coil, both the torques are same, and when that both the torques will remain same, so you will get it here as a number of tau dash must be equal to tau double dash at equilibrium position, so it will be written as a NAIB must be equal to that of your K5. and therefore I can write down this phi can be written as NAB upon K into I. So where this N is nothing but the number of turns, A is nothing but the area of the coil, B is nothing but your radial magnetic field, and phi is nothing but the deflection of the coil. So I can say that phi, that is the deflection of the coil, is directly proportional to the current. And this is to be called as your principle of moving coil galvanometer. So using that principle, this moving coil galvanometer is constructed. Now in that, this coil consists of number of turns N, area of that coil is A, and current flowing through that coil is nothing but I. So from these three physical quantity, that is number of turns, area and current flowing through that coil, you will get one of the physical quantity which already you have studied in 11, that one of the physical quantity is present, which is to be called as a magnetic dipole moment. So the magnetic dipole moment of the coil, current carrying coil, this magnetic dipole moment of current carrying coil is denoted by letter mu, and this mu is nothing but number of turns multiplied by area multiplied by E. So this is nothing but the magnetic dipole moment. Now this magnetic dipole moment has the same unit as that of your electric dipole moment. So already you have seen the electric dipole moment also, you have seen magnetic dipole moment also. So if you are remembering, in your previous 11th standard topic, in the topic as a magnetism, you have seen magnetic dipole moment for a bar magnet having two poles, as a north pole and south pole, having pole strength plus M and minus M, separated by a certain distance as a twice M. So magnetic dipole moment small m can be written as capital M as be written as small m into twice M. This is a magnetic dipole moment of a bar magnet, and this mu is nothing but the magnetic dipole moment of a current carrying coil. Both has the same unit as a ampere meter square. So unit will remain same, but the formulas are different. Now such current carrying coil, whenever it is kept in the uniform magnetic field, is just now whatever we have seen, current carrying coil is kept in the radial magnetic field, it will experiences a torque. That torque tau is equal to N A I into B into sin theta. Out of that, N A I is nothing but your mu quantity, B sin theta. That is nothing but the torque. Therefore, I can say that torque is a vector quantity which is equal to vector mu cross vector B. And from that, I can concentrate on maximum torque and minimum torque by putting certain condition on theta. Theta is the angle between this mu and B. So if your theta value is equal to 0 degrees Celsius, means direction of magnetic dipole moment is parallel to the magnetic field. Direction of magnetic dipole moment is parallel to the magnetic field, means angle between them is 0. At that time, sine of 0 is 0, and therefore torque acting will be become as a 0, which is a minimum torque. But if your direction of mu, that is magnetic dipole moment, is perpendicular to that of your magnetic field, so your theta value will become 90 degree, and your sine 90 is always 1. So your torque value will be become as a maximum, which is equal to nothing but mu B. So this is about the dipole moment, magnetic dipole moment of the coil, and torque acting on that current carrying coil, its maximum value and minimum value. And now we can concentrate on the potential energy of the current carrying coil. So now that potential energy of the current carrying coil, for that purpose, we can say that Already in electrostatic you have seen potential energy of electric dipole, that you have seen. So potential energy is denoted by letter U, which is equal to nothing but minus PE cos of theta. That formula we have seen. Now we want magnetic energy of magnetic dipole moment. So now that magnetic energy, now in equivalence with this electrostatic, I can write down magnetic energy as a U, which is equal to nothing but minus. Now magnetic dipole moment is mu, magnetic induction is B into cos of theta. Now using that quantity, now we can say that the maximum value of mu and minimum value of mu. So now if I am saying that this is the direction of magnetic dipole moment, here is the direction of your magnetic field, both are parallel to each other. So when they are parallel to each other means theta value is equal to 0 degree, and if theta value is equal to 0 degree means cos of 0 is 1. So your potential energy will become as a minus mu B, which is a minimum potential energy. But if we take a reverse case, in that reverse case, the direction of magnetic dipole moment and direction of magnetic induction, they are anti-parallel to each other. Anti-parallel to each other means theta is equal to 180 degree. And in that your cos of 180 is minus 1, and then your potential this magnetic energy will become as a minus mu B into cos of 180 is minus 1. Minus minus will become plus. So your magnetic energy will become maximum, which is equal to nothing but mu B. So this is about the magnetic energy. So now we have seen two important concepts. One concept is about the mu, that is your magnetic dipole moment, which is equal to product of number of turns, current and area. Then we have seen a torque, which is equal to, torque is a vector quantity, so vector mu cross vector B. From that we have seen maximum value and minimum value, and also we have seen the magnetic energy, which is denoted by letter U, which is nothing but as a UB plus minus. Means it is maximum when your angle is 180 degree, so your magnetic energy is plus, and it is minimum when your U energy, that is magnetic energy, is negative. And this is about this three physical quantities. Thank you.